it look good?
Sure.
Okay, perfect. So, hello everyone, and thank you for coming. I hope you all have been staying warm during the freeze. I'm Kenneth Shipper over at University of Houston, studying geophysics. I'm very happy to share some of my latest research with you all in Guyana Suriname. But I really wanted to thank those at HGS for making this possible and giving me a chance to share this research. If you have any questions afterward, feel free to email me with this email address or on LinkedIn. I'd love to continue the discussion. Okay, so just a little bit about where we are. Oops. Okay, sorry. Okay. A little bit about where we are here. The Guyana Suriname margin, it thins from this 40 to 50 kilometer thick elevated arcing greenstone to the southwest into this Jurassic age oceanic crust. So to the northwest, the Barbados Accretionary Prism truncates this margin. And to the southeast, the basin is abutted against a volcanic margin, which dips along strike. This area, the Demerara Plateau, exhibits SDRs or seabed dipping reflectors up to 25 kilometers thick and dips to the northwest. Lastly, the Demerara fracture zone separates the Jurassic and Cretaceous oceanic crust, creating during the Central Atlantic and Equatorial Atlantic openings. So the basin has seen extreme success, especially in the Stalberg block, since the Liza discovery in 2015. The block went from 276,000 barrels per day in 2022 to 353,000 in 2023, and is expected to exceed 1.2 million by 2030. Suriname currently averages 15,000 barrels per day, but is expected to begin ramping up with discoveries in blocks 58 and 53, which neighbor the Stalberg block. Unlike the rest of the Equatorial Atlantic, the Guyana-Suriname Basin has its unique set of challenges due to this prior Triassic to Jurassic rifting phase. These primarily include uncertainties regarding the timing of volcanics and underlying unknown crustal parameters. This study aims to model those specific parameters and study their effects on the resulting petroleum system. Underlying the deformation and emplacement of these volcanics along the Demerara Plateau into Guyana and the continent oceanic transition of the crust may have some really strong implications for the limit of exploration as we continue to go further and further offshore Guyana Suriname. The tectonic origin of the Guyana Suriname margin begins with the Central Atlantic opening, separating Guyana Suriname and the Bahamas. One of the challenges with understanding this opening is the lack of data in the Bahamas and the conjugate here. The thick carbonate platform reduces seismic penetration, and there are only a few wells drilled there. I've recently done some work on studying this area and figuring out the crustal transition from northwestern Bahamas into southeastern Bahamas. And I've pretty much found some potential for matching volcanics, oblique rifts, and similar crustal tapering that you see in Guyana Suriname. The volcanics in Guyana Suriname have been drilled at the Demerara Plateau and date to 173 MA. The extent of these volcanics is mainly evident by the seaward dipping reflectors in the seismic. I have run a gravity inversion to estimate the density contrast of these dense volcanics in central Demerara Plateau, and the inner SDRs here, to the less dense, partially chaotic, or classic outer SDRs here. So following the Central Atlantic phase, there's another rifting phase during the opening of the Equatorial Atlantic between Africa and South America. This resulted in transpression along the Demerara fracture zone, as well as basin-wide erosion. Okay, just to give you a little bit of the geologic setting there. So here's a comparison of the petroleum system from northwestern Guyana to southeastern Suriname. There are three primary source rock intervals. You first have this Jurassic to Aptian Lacustrine shale source rocks with TOC of 1.5 to 2.5%. And these would be dependent more so on the underlying basement fabric as far as their presence. And these are very relevant in the Demerara Plateau. And then you have this Aptian to Albion interval. These are more dependent on carbonate shelf stratigraphy as well as erosion that occurred during the Equatorial Atlantic opening. And then lastly, you have this Albion to Santonian type 2 to 3 source rocks with 2 to 15% TOC, defining the Conchi formation. These generally thicken basinward, which is characteristic of many passive margins. So with increasing distance from the local conjugation, one of the prevailing challenges in exploration here is determining the effects of the continental oceanic transition and extent of the Triassic to Jurassic volcanics. The prominent reservoir intervals as well are the Lake Cretaceous with these deepwater clastic channel and fan complexes, specifically in the New Amsterdam Formation. but there are also some late Cretaceous carbonate reefs, like we see in the Rayford Seamount, as well as some minor Paleogene reservoirs. And the primary seals are these late Cretaceous deep water shales, which create these nice stratigraphic terminations. Okay. So the play fairway in Guyana Suriname has primarily been along this northwest to southeast shelf trend, extending from the Stopford Block into Block 58 here. Fields like the Uru, which is set to begin production in 2026, the Yellowtail in 2025, or the Whiptail Development Plan, which combines tilapia, pinktail, and whiptail discoveries, have an estimated capacity of 220,000 to 275,000 barrels per day, and will have its first oil slated in 2027 to 2028, show that most of the interest and upcoming production trends remain in this play fairway in Guyana. So exploration interest remains strong in the Stopford Block. Additionally, with more discoveries like the Seabob 1, Kiru, Finktooth, and Lau Lau discoveries. The play fairway extending into Suriname's Block 58 is also said to have an increase in production with the Maca Central, Kwaskwasi, and Baja discoveries. However, there is still much to explore outside of the centralized play fairway. While there have been numerous dry holes, there has also been some oil and gas shows. So this study tries to de-risk these areas by first modeling the effects of the continental oceanic transition in crustal thickness on source rock maturity, and then as well as integrating the volcanics into the basin model and study its effects on source rock maturity. So these two objectives may have some implications for exploration with this northeastern area with blocks 53, 45, 54, and 47 in Suriname, as well as the Kanji block in Guyana. The most important takeaway, though, is showing how crustal thickness, type, and the effects of volcanics on tectonic subsidence all affect the Guyana Suriname basin. Okay. Okay. So I'd really like to thank those at Explore Lab for their help and access to a new software that I'll be using for this study that somewhat sets it apart. It is called Excalibur. It essentially uses machine learning to estimate the solution to the heat flow equation. In a typical conventional simulator, you would create a forward simulation with a finite volume based off your boundary conditions and constrained to some temperature data. Excalibur essentially uses deep learning to do this based off an initial training set of finite volumes with boundary conditions. Another thing that this study will be using is standard thermal stress instead of Richard reflectance. So standard thermal stress is a measure of the time temperature integral that causes chemical reactions that result in petroleum exhalation. It is independent of kerogen type, most importantly. So different kerogen types expel at different thermal stresses. So in this study, we mapped the kerogen effect by simply adjusting the color bar with the temperature correction you're seeing here for the expulsion onset. So instead of computing individual functions to describe basin parameters, Excalibur sets up a neural network of a coefficient for each function that is then ran through a conventional simulator. And this results in a very fast computation, which is particularly useful for academics like me who don't have these high-powered industrial computers. It's also used in this work to develop a regional 3D basin model where you can really test these lithospheric parameters like RHP, volcanics, the timing, their extent, and other parameters. Okay, so this is the data that has been used in the study. My largest constraint here is definitely the seismic. It keeps the study pretty regional. It's based on these sparse 2D lines in the Janaury Plateau. And in the Stopford Block, it's very nice. TGS really made this research possible as they gave me access to some nice 2D KPS scheme grid within the Stopford Block here. So I interpreted 6 horizons within there. And afterward, I ran a MOHO inversion to characterize the MOHO. One of the results of inversion is it's really just a tool for you to learn. You know, in this case, we had crustal abnormalities in the resulting MOHO inversion that could be interpreted as due to density variations within the volcanic units. So that's how we defined that volcanic classic transition from Janaury Plateau into Guyana. Another, obvious characteristic is relevant in the seismic. You can see some strong high amplitude subparallel chaotic reflectors in southeastern Guyana that dim to the northwest, which may be a function of increasing clastics. Okay. Oh, and another primary difference between southeast Guyana and northwest is the shelf slope. Through the process of backstepping, you can see more accommodation space is made towards the southeast, which could be attributed to the equatorial Atlantic opening. And then you see this major depot center along the Guyana Suriname border and in the Lake Cretaceous. So here are some more basic modeling parameters. It's constrained by these Horner-corrected temperatures. Here you can see the temperature from the literature at each well and the associated geothermal gradient. An important parameter that this study focuses on is radiogenic heat production. It's why the continent oceanic condition is so important, as oceanic crust has near zero RHP, whereas continental crust is non-zero and varies quite a bit. The reason we want to know this variation is because, as you can see here in this transformation ratio to age plot, a 1 microwatt per meter cubed increase in RHP results in a 40 million year earlier generation of the first petroleum. So it's important in determining your critical moment and the whole petroleum system. Each of these 1D models has a calculated RHP value, which is interpolated here on the right. We essentially varied RHP until the geothermal gradient matched these the temperature controls. One important note I'd like to make on this RHP map that I want you to keep in mind in the future is that it's a lot less along the shelf toward their Paima and Essequibo. Okay. So lastly, the other parameters are shown here. The difficult one is lithophases. This is mainly because we didn't have any lithology. We have really no well control on oceanic crust that's in the public that we could use. So we tested 0 to 30% quartz because we don't know the lithologies, and that seemed like a reasonable range. And what I'll be showing you today is the 30% quartz case. And this is because this would be the worst case for source rock maturity. And this is just on oceanic crust. Okay, and then these are some of the other initial basic parameters. All right, so here is the resulting 3D basin model. So on the left here is overburden thickness from the 3D model. Keep in mind that this is very regional trends in the Demerara Plateau, and a little bit more accurate in the Stavert block due to the limited seismic data. You could see the Upper Cretaceous to Miocene depot center trends. There's really two within the Barbados secretionary prism, all the way down to the play fairway in here, and then in southeastern Demerara Plateau. And there's some smaller variation offshore Suriname here. Those trends very closely match the resulting standard thermal stress, with red being in the gas window, green is in the oil window, and blue being immature. You could see increasing maturity with overburden that again follow this northwestern trend and down in Suriname. The Santonian interval here is meant to show the uppermost section of the Kanji formation, again showing the worst case scenario for source rock maturity. So where standard thermal stress doesn't quite follow that overburden trend, it can be attributed to an increase in clastic input in the volcanic unit section, as well as a reduction in radiogenic heat production to the northwest. So this is where the effects of the lithosphere come into play and affect the petroleum system. You can see this rapid immaturity along the shelf here. And again, this can be attributed to a decreased RHP, as we saw previously with the near Arapaima, and an increase in clastic input in the volcanic unit section. The opposite, though, is true in offshore Suriname, where it's shown to be a lot higher standard thermal stress. And then lastly, one very important note I'd like to make is that this just represents a possible kitchen extent. There's no public temperature data on oceanic crust, so it's difficult to actually constrain a limit. Okay. On the left, we have a map of regional overburden thickness since the Albian now. So we're going down to the base of the Kanji formation. The overburden trends have the same extent, roughly, as the Santonian interval, but in this case, they reach a maximum thickness of 10 kilometers. And you can sort of see that effect with more gas with more areas being in the gas window here. So in Guyana, the kitchen extent increases a little bit to the northeast by about 10 to 25 kilometers. And then in Suriname, it is about 50 to 75 kilometers to the northwest from the central Damara Plateau. Again, keep in mind, limited seismic coverage, no temperature data on oceanic crust. But the most important trend here is this increase in maturity towards the shelf and from offshore Suriname into the Damara Plateau. Okay, now let's compare this to some actual known oil and gas fields and discoveries. You can see within the play fairway, there's a trend of oil to oil and gas condensate from Guyana to Suriname. This ranges from oil fields of like Hammerhead, Lisa, Yellowtail, Tupo, and then in the gas condensate window, Hajmara, Maka, and Sapakara. Slovenia is also a gas discovery just to the east of the Kaskasi field in blocks 53 and 52. But overall, the model matches pretty well. It's a little bit more mature than predicted, especially in southeastern Stauberg, where it just reaches the condensate window. But it's very accurate near Lisa, in Yellowtail, as well as in Block 58. So let's talk about outside the play fairway. Along the shelf, there are several fields like the Kapara field, which are in the immature window in the Santonian, but just reach oil window in the Albion. The Damara Plateau here exhibits this transition from oil to gas, with the furthest oil show being that limits of maturity. And keep in mind that some of these areas in the Damara Plateau target deeper source rock intervals below the Albion. And then lastly, the dry holes outside the COB, especially in the Kanji block, are in the oil window. And there is one oil show down here that supports that. Okay, so keeping along the same line of looking outside the play fairway, there are multiple prospects that have been pointed out in the Van Elsen-Comberg article. I've just overlaid them here against this regional Paleocene to Santonian reservoir thickness grid from the 3D model. Generally, these prospects stay away from the thick depot center and along the play fairway here. So before getting into the more interesting Lake Cretaceous prospects that the study focuses on, there are some Jurassic prospects in many basins local to the Damara fracture zone, and some Cenozoic ones along the shelf. And you also have early Cretaceous, this dark green here, that are more up dip of the on the Damara Plateau offshore Suriname. So the Lake Cretaceous prospects here extend along the Damara Plateau shelf slope. The reservoir thickness seems to match, especially in block 52. It's a little bit thicker there, and 53. So this area is very prospective. Okay, and comparing to the basin model, you can see that the oil window reaches the limit just along the Lake Cretaceous here in the Albion, in blocks 48 and 42. And along this shelf, the low RHP results in a more immature area along the majority of the prospects in Damara, Oranduik, and Kanaku blocks. In this model, these would target more so early Cretaceous source rocks. They'd have to. But keep in mind, it's a really low RHP, almost abnormally low, to the northwest. Let's see, in block 42, I'm going to mispronounce this, but the Zindirij 1 well was non-commercial, which showed potential for a working petroleum system. And in blocks 52 and 53, where it's really prospective, Petronas has recently made an oil discovery at Rostonia there. This lines up well with this 3D basin model, especially in the Santonian interval. And lastly, the Kanji block is of interest. It has seen some non-commercial hydrocarbons in Bulletwood and Sapoti. So this is on the edge of the oil window, especially in the northwestern area here where they were drilled. Okay, so to conclude, we built a basin model which takes into consideration some parameters that were previously unknown, including crustal thickness, RHP, and volcanic timing and extent. The basin model roughly coincides with known production trends. It indicates a trend of oil window to gas window along the main play fairway from Lisa to Slovenia, while having limited seismic coverage in the Damara Plateau and no temperature controls on oceanic crust. The basin model does indicate the maximum pitching extent to occur really along this Kanji block or down here along this Kanji block into blocks 42 and 48. Let's see, along the carbonate shelf, there's an increase in immaturity, which is likely attributed to a strong decrease in radiogenic heat production and an increase in the clastics in the volcanic units. Most prospective areas here within Block 53 remain prospective with the source rock well within the gas to oil window. Then lastly, the crustal and volcanic parameters included in the study may provide some insight into some of the disappointments in the Kanji block. And I really hope that it provides some ideas for those of you doing your own modeling in Suriname and on the Tamar Plateau as you focus and head more offshore in these late Cretaceous prospects. So thank you all. I'll be happy to take any questions. Thank you.
So rather than use the chat, why don't we just use the hand? Is there someone who would like to raise their hand rather than do the work of typing into the chat? Anybody want to raise their hand with a question? I guess my question for Ken, just to start off, is I'm really interested in this eastern area. It's not got very many wells in it, and they have shows, but it's got all the red. And so what do you think about the area to the east? And I don't know what the structures are out there. Is it not mature, or why is it not been productive so far?
My take is that it's more structurally dependent. There's been this basin model really relies on just a couple regional lines here, so it's difficult to see that structure. Maybe I have one line that I could show you. Here. Yes, you can see along here. I think it's much more structurally dependent. Most of my models within the gas window, I think it's very prospective for the future, though. Yeah, I don't know.
So anybody else want to raise their hand, ask a question? Oh, Joe, how about you? Go ahead.
Hi, good evening, everyone. Thank you very much. Very nice talk and overview. One question I have is, did you have any access to any oil and gas show data? And if so, any geochemical data?
No,
Okay.
nothing like that. Yeah.
And,
Just the go ahead.
sorry. In your model, and you mentioned your basin model using machine learning based on your TGS data sets. I'm quite interested in how, with your horizons, you upscaled properties in the model.
As far as determining the surfaces within the 3D model, that was essentially, as I understand it, you'll have to talk to some of the people that work at Explore Lab. That's essentially an interpolation between the 6 stratigraphic horizons that I've interpreted within the Stopper block.
Okay, sorry, and just in terms of from source rock intervals, which you walked us through the 3 regional, sub-regional known source rocks from DSTP and obviously new discoveries, but from those properties, could you say a little bit of how let's say the richness and thickness of those, and then to reservoir units, if at all, was that done in the model, or is this purely the thermal model and timing?
Oh no, this is purely the thermal model and timing. Yes, sir.
Okay, thank you.
Okay, I'm looking through. Anybody else? Can you raise your digital hand or your actual hand for one more question? Okay, Charles Sternbach has raised his actual hand.
Hello. So,
Oh, hey.
hey, Ken, great job. Wow. So, is there deeper potential? You mentioned maybe some deeper untapped objectives. Tell us a little more, please.
Yeah, sure. Okay, so this is from the Nelson Combrick article, these prospects. You can see some Jurassic ones, especially towards the Timor refractory zone, where you have these rifts and mini basins that form during the Atlantic opening.